All right, now thank you. Yeah, I thought I just resume it, but anyway, so it's not user friendly. So once we define alpha t to be weight of minimum weight vertex cover of t, we can try to get a recurrence relation for alpha t with respect to alpha value for a subtrace, right? So that's very natural way to do it. So let's see. So we can write alpha t. So based on its Trojan, so here we have alpha 1, alpha 2, up to alpha tk. So let's see. Unfortunately, there's a big question mark. So it is at most, I think, but equality does not really hold because minimum size one may be, oh, sorry, this one plus the root. Now, the problem is once we write this, whether do we use this vertex or not, it's a headache. So that is how to cover these edges. It really depends on whether optimal solution for T1 through to TK, whether they use these vertices or not. If all these subtrees use their root, if all of them use this root, then we don't need this one. If do not use this one, some of them do not use this, do not use their root, then we have to use R. So here, whether this equality is this one or should plus weight of R, it's not clear. So actually, we were not able to get a recurrence relation for alpha t in this way. So that's the reason I want to talk about this example, to show you different aspects of dynamic programming, something different for dynamic programming here. So here we define the value, but it seems we're not able to get a recurrence for this one. So it looks very nice. The structure of the subproblem is very natural, and we should have a very good connection. All right. A solution is not unique. Solution is not unique. It can have many optimal solutions. So what we do? So in order to do that, actually we define another value in order to resolve this issue. So define another value, beta of t. So that will be let's see. My notes may be something wrong. Let's see. Okay. Okay, but anyway, let's define another value. And suddenly I spot notes, maybe there are some typos there. Okay. So beta t is weight of minimum weight vertex cover of t that use the root. Okay, so beta of t, it's a value of special vertex cover. So for t, that's t. So let's look for special vertex cover. It uses this vertex for sure. So among all vertex covers that uses this vertex, this vertex cover achieving the minimum value. All right, now we define alpha and the beta of t in terms of alpha beta of smaller its trojans or subtrees. So now what we try to do is define or obtain recurrence. Yes, there may be a silly typo in the notes. I'll correct it later. Okay. So that's something different. That's what we are going to do. All right. So it's not only one value, two different values. We define these two recurrence for these two values simultaneously. So let me erase something. So you remember, we remember definition of beta and alpha, okay? So remove them. Okay. So it's more like a system of equations now. So what is beta? How can we define, obtain a recurrence relation from beta t? Beta t will use the root for sure. So it will use the root for sure. So it's weight of r, because we have to use this vertex. All right. Now, once we use the root, then all these edges are covered. Then for these subtrees, we only need to consider optimal vertex cover for these subtrees. It does not matter whether it's use root of these subtrees or not. Therefore, beta t equals this one, plus for each of them, the minimum one will be alpha ti. So here I equal 1 to k. So we obtain a recurrence for beta in terms of alpha ti. So that's R. Okay. Then similarly, we obtain it for alpha of t. So what is alpha of t? It's either use the root or do not use root. So it will be minimum of using root. Using root, we know it's beta of t. If it use root of t, or do not use root. If it does not use root, so if it does not use this vertex, so how do we cover these edges going out from R and connected to R? We have to use these vertices. Sorry. So we have to use these vertices. Roots of these subtrees, all the roots must be used. All right. So otherwise, we have to use all of them. So that way, beta value. No need. Actually, when paired, if you look at the subtree, if we use the R, then for subtree, no need to use the roots. Does not matter whether it's used it or not. But if the for the whole tree you do not use R, then you must use roots. All right. So that's a case. That's a situation we do not use. We do not. So we use the root. So that's a situation we use the root R. So in this case, it does not matter whether we use roots of subtree or not in the vertex cover. And this situation when we do not use the root. If we do not use root, we must use the roots of subtrees. So these must be used. All right. So the optimal value for alpha for t will be minimum of these two possibilities. Either use the root, so let's use R, or this one does not use R. So two possibilities. All right. So we get this recurrence relation. So that shows you a different side of dynamic program. Sometimes in order to compute one value, we need to define more values and get recurrence relation for all of them. All right. So once we have this, then we have a dynamic programming algorithm to compute beta and alpha values from bottom up. Our definition of beta t, the equation definition of beta t, I said beta t equal minimum or something. That's one maybe not quite, not a very good way anyway. Okay. Oh, actually, the definition is correct, but it's a tedious way. Actually, definition is all right. It's somehow weight. It's not really a typo, but it's easier to use word to define the beta of t. Okay. Actually, it's correct. It's not incorrect. I just look at the notes. All right, but it's too tedious to write in that way. All right, so let's convey the idea of show you different aspects of dynamic programming. All right, okay, I think that's it for these two examples. Any question about dynamic programming? We're almost finished about dynamic programming. Okay, all right, now we try to see how we can solve the clique problem, perhaps using idea of dynamic programming to see if it's possible to solve more problems using dynamic programming, and eventually lead us to hardness of problems, NP completeness, theory of NP completeness. Okay, so let's see. So let's try to see whether we can use dynamic programming to solve clique problem. So we want to know what find the largest clique, or what we want to know maybe say find the largest clique. All right, so find the largest number of vertices that form a complete graph. All right, so for a graph, there's one number called the clique number, denoted by omega g. So that's the size of largest clique. Let's see how we can compute omega g. So that's optimal value, how to compute. Okay. All right, so let's consider particular vertex V. Using idea of dynamic program for many problems like subset sum and our previous example. So consider largest clique. It's either including V or does not include V. So only two possibilities, right? So it has neighbor. So here the neighbor of V. So largest clique. So maybe K largest clique. Let's see. The reason I use K because the complete graph we use Kn to denote the complete graph, like K5, K6, Kn normally. So sometimes I use K for the cliques instead of C. They may confuse with cycle. All right. So largest clique K. So there are two possibilities. Either V is in K or V does not in K. Right? So that's graph G. So if V is not in K, so that means we reduce problem to G minus V. So we never use V. We can throw V away. If it belongs to K, then actually we reduce problem to the graph induced by its neighborhood. So we only need to consider this part. Because clique has all possible edges. So any vertex has no edge with V can be thrown away. All right. So what does that mean? That means omega of G equals maximum of G minus V plus, sorry, this one or maximum of these two. So this one will be plus 1. So you see, it's very easy to get a recurrence relation for computing the size of largest clique. So that's called the clique number. So this one is called the clique number. Okay. Now the question is, can we use it to compute clique number efficiently? So I mean, whether we can do it in polynomial time. Well, this one needs a polytime algorithm. All right. Now, in order to compute this recurrence relation, if you use top-down approach, because if we look at the click number, so here, if click number here, oh, sorry, here I forgot to put click number inside, sorry. Should be, no, here the typo. Here the real typo here. It's omega, okay, forgot. So here's omega. If we look at the size of omega here, so here if size of omega maybe so it's say let's use a value here k here. So here value is k, here is k minus 1. So in terms of the recurrence relation, if you look at the solution size, here is k, so if t of k depends on this one, here is tk, here is tk minus 1. All right. Now, because number of verses, if you also want to put it in, that will be two-dimensional. So here, the problem size will be, if we put n inside, so here n, so dependence here will be n minus 1. Number of verses reduced by 1. So here, the number of click size is reduced by 1, but number of verses is also reduced. It can be reduced by many, but in the worst case, it's just reduced by 1. So if you look at this recurrence, since n is only reduced by 1, k is reduced by at most 1. So that is not good. If we use top-down approach, basically time it takes will be this much. All right. Sorry, even worse. Actually, it's even worse. It's even worse, actually. No, it's not only depend on the click size. Yeah, it's actually 2 to n, because this one it's k. It's not even reduced by 1. So it's in the worst case, it's 2 to power n, because this one k is not even reduced by 1. In the worst case, it's 2 to power n. So dynamic programming does not really help us at all. Okay, but of course, you say, why do we use top-down approach? Because it's not good. We can use bottom-up approach to compute this recurrence more efficiently, avoid overlappings. All right. Now, how can we find the ordering for our computation? So if we use bottom-up approach, then we need to find ordering to compute this recurrence. What kind of ordering will be useful? So we can try use our previous idea. Suppose we order verses. So V1, V2, up to so Vi up to Vn. All right. Now suppose this V, we focus on this part. So we focus on this part as sub-problem. So when we want to compute click number, we compute click number of subgraph in this fashion, right? Now, so this one, this part is okay. G minus Vi. So we focus on this part. So that's a sub-problem. But problem is with this part. This part, its neighbor can be scattered around. So this neighbor versus in its neighbor may not be consecutive at all. If it's a consecutive, then we can do it. But problems they are not consecutive. So there are other verses in the middle. So that's the neighborhood of Vi. So these are neighborhood of Vi. So we want to know the click number of this one, but this one has not been computed. How do we compute them? It's not consecutive. So that's a headache. We don't know how to do it at all, because we cannot organize things away so that neighborhood. So then the next question, of course, is it possible to order verses so that if we follow particular ordering, all its neighbors will be consecutive? If we can do that, then we can define subproblem. The total number of subproblem is at most n squared. So that would give us polynomial time algorithm. But unfortunately, no such ordering is possible in general. So therefore, so we can have a recurrence relation for clique or for clique number in a very nice way. It looks quite nice. But unfortunately, because the independence, its dependency on k and n is very bad. The total time, if we use recurrence to compute clique number, it's basically 2 to the power n. It's basically exhaustive search, try all possibilities. So that will not help us at all. So next question is, then is it possible to compute clique number in polynomial time at all? Okay, so the big question is, can we compute dynamic programming seems to not work, but maybe other ways to design algorithm. It's endless. There are many different ways. Is it possible at all? I strongly suggest you to see how fast you can find a 3-click, a very special case. To find a triangle, how fast you can find a triangle in a graph. Can you do better than n cubic in the worst case? So that's basically it's exhaustive search, n cubic, of course, because only 3 verses. So that's very special case. In general, we want to find a k-click. So it's kk. Here, k equals 3. I strongly recommend you to try this problem after class to get a feeling of the subtlety or difficulty of finding a k-click. So even for finding a triangle, it's difficult to do better than n cubic. Of course, you can do it mn, but in the worst case, the same, because m can be order n squared. All right. So to really beat n cubic, it's not easy at all for finding a triangle. So that suggests maybe it's very difficult to find a clique in polynomial time. So big question, can we prove it? All right. So that's next thing we are going to discuss, called the theory of NP completeness. The purpose is to show that certain problem is not likely to be solvable in polynomial time. The purpose of this one is to prove so that's a purpose of theory of NP completeness. So far we have seen quite some examples that admit polynomial time algorithm. We can design polynomial time algorithm to solve these problems. But unfortunately, in practice, most of the problems we need to solve in practice do not seem to admit polynomial time algorithm. I cannot say absolutely that these problems cannot be solved in polynomial time. But what we can prove is it's very, very unlikely that these problems can be solved in polynomial time. So that's a framework of NP completeness. We are going to develop a framework that will enable us to prove that many problems cannot be solved in polynomial time, unless something very, very unlikely happens. All right. Of course, it would be nice that we can prove with certainty that the problem cannot be solved in polynomial time, just as we can show that certain functions they do not have root, integer as root, or do not have real number as root. But in this case, it's extremely difficult. No one knows how to prove it. If anyone can prove it, you will get at least $1 million. Much more than that, I think. That's the biggest open problem in mathematics and computer science. All right. So what we can do is to show that it's not likely that certain problem can be solved in polynomial time, including the problem of computing the clique number of a graph, same as finding largest independent set, finding minimum vertex cover, find the longest path, and many more problems. We can show that it's very unlikely they can be solved in polynomial time. The idea is the following. In order to prove something is difficult, how can we prove it? So if we want to show that something is different, it's difficult. How can we do it? Maybe certain work. So some work is too difficult. So a boss asks you to do some work. So you want to prove that this job is impossible. There is no point to push me to do it. I cannot do it. It's too difficult. Actually, one way is to show maybe the budget is not enough if you can do that, right? So if the boss asks you to get a new computer with $10, so you must be crazy, right? It's impossible because $10 is certainly not enough, right? Another way is to show that I cannot say it in absolute term, but I can show you that if I'm not capable to do this work, but I can show to you that all other people, many other people are not capable of doing this work. So even they're very famous people, very like smart people, if I can show you this job is it's also hard for them. If I can do that, so if I can do, you can show that if it can be done, then something unlikely happens. All right. So you can show to your boss, maybe I cannot do the job. And also all of these people cannot do the job. Even 1,000 people, a lot of people cannot do this job. So that will be good enough to show that strong evidence that this work is difficult. So you may not be able to show that this job is difficult, but you can show that this job is difficult for me and difficult for many people. So if 1,000 people is not enough, you can show that it's difficult for 10,000 people. If it's not enough, maybe 10 million people, 1 billion people. Then that will give very strong evidence that this work is indeed hard. So that approach is to what we're going to take. So give very strong evidence. So in order to do this, what we are going to do is give very strong evidence. Very strong evidence. Maybe instead of work, I say job. Okay, so instead of work, so maybe here it's better to say job. So a particular job is hard. So in order to prove that a particular job is hard, what we're going to do is give very strong evidence that the job is hard. We cannot prove that job is hard in absolute terms, but we can show and we can give very strong evidence that the job is hard. All right. So that's what we are going to do in the theory of NP-completeness. My understanding is many of you have taken the formal language course, right, last term. Am I right? And the subject has been discussed in that course. So you can regard this one as a review to see two different instructors have different perspective, or will teach this in different ways. So you can regard this one as a review, right? Some of them don't, so I still will teach this part. If you have Learn these things, you regard this one as a review for next 2 weeks. Oh, okay. Yeah, in terms of next 2 weeks, actually, I just realized, I said we have plenty of time, but actually we don't. I suddenly realized when I checked the university calendar, actually there are no course, almost no course classes for next 2 weeks because of reading week and East holidays. But anyway, I have to reorganize things. I think should be okay. All right. So going back to theory of NP-completeness. So that's our focus. Polynomial time, we try to define a design efficient algorithm. Now, the purpose of NP-completeness is to show that certain problems are difficult. All right. Okay. So in order to do that, we have to have something little bit formal. So I try to avoid that kind of formality because that would be too mathematical and too messy. I try to stay at high level, at the problem level, not to touch, not to do the formal language level, but we have to touch that part. Okay, it's related. So let's consider problem. To design the algorithm, we focus on particular problem and design a particular algorithm. Now, if we want to show that a problem cannot be solved in polynomial time algorithm, we have to rule out all possibilities of polynomial time algorithms. That's, of course, very difficult. So we have to get things a little bit formal to restrict our attention and focus our attention to certain, under certain framework. All right. Of course, our object will be algorithmic problems. So we have input and output. Through an algorithm, we get output. So that's our algorithmic problem. Now, algorithmic problem, typically there are three types. One is decision problem. Another one is optimization problem. And another one is called search problem. Or we can say decision version, optimization version, or search version. For example, click problem. We use click problem as example. Decision version just want us to know whether a graph contains a click, say at least size k. So answer will be yes and no. Optimization version, we want to compute its click number. So it will be a number. All right. And search version, we want to find a largest click. So each problem actually can be formed, has or is related to three different versions. So we can see three different versions or three different versions. One decision version, the answer will be yes and no. One optimization version, we just want to find the value of our optimal solution. So that's just the value of an optimal solution. And then search version, we want to find an actual optimal solution. All right. Okay, now if we consider these three versions, which one is easiest? Which one is difficult, hardest? Of course, easiest version is this one. Among these three versions, this one is easiest. Once we know how to solve the other two versions, we know how to solve decision version. You can answer either yes and no, right? Once we find the optimal solution, of course, we know how to answer this question. So among these three, decision version is easiest. Now, when we try to design an algorithm, of course, we should try to focus on search version. When we try to design algorithms, we try to solve the most difficult version. Now, when we try to focus on the non-existence of certain algorithms, then we should focus on decision version, non-existence. if we can show that decision version do not have polynomial time algorithm, of course, then the other two versions will not have polynomial time algorithm at all because they are more difficult. All right. So as far as the theory of NP completeness is concerned, we will focus on decision version. So as far as this one is concerned, we only focus on decision version only. We don't need to consider the other two versions. So from now on, all our problems will be decision problems. The answer will be yes and no. All right. So problem is easier. We don't need to looking for an optimal value or optimal solution. Of course, in order to answer yes and no, we may need to really find an optimal solution or compute optimal value. But the problem we are really focusing on are decision problems. Its answer will be either yes or no. The problem is easier, just yes and no. All right. So output has a single bit, 0 or 1. All right. So that's decision problem. All right. So actually now here is something little bit formal. So formally, how do we define a decision problem? So typically a problem has two parts. So a general description of the problem. Or parameters or arguments. So here are parameters. Then properties answer needed to satisfy or solution needed to satisfy. So typically a problem consists of two parts. A description of parameters or arguments and the properties a solution need to satisfy. So let me give you a concrete example how we define decision problems. All right, so for clique problem, so typically we will give a problem a name. So here we call it a clique. So then each individual instance will have following parameter involved. So it's contain a graph, input will be a graph, and a positive integer k. So here, clique problem has two parameters. One is a graph, and another one is the integer k, positive integer k. All right. Now we ask a question. Because decision problem, we ask a question. So that describes the property our solution need to satisfy. So does G contains a k clique? Contain. All right, a complete graph, subgraph on K vertices. So that's how we define a decision problem. So we specify, we have a general specification of its instance and then ask a question. A particular instance is obtained by given particular values for its parameters. So once we give its a particular value for its parameters, then we get an instance. So for example, here we have an instance of a clique problem. So maybe k equals 4. So that's a particular instance of a clique problem. All right. Okay. So this is how I define the decision problem. Let me give you one more example. Say clique problem. Sorry, vertex cover problem. So instance, again, it's a graph, undirected graph, a positive integer k, and question, does G has a vertex cover of size at most k? All right, that's a decision version of vertex cover. Okay. Typically for clique, maybe we'll say as a clique of size at least k. Typically, because that's a maximization problem. So the clique is a maximization. Here the maximization problem. Clique vertex cover is minimization problem. All right. So as a decision version, maximization version typically is phrased in this way. Minimization phrased in this way. All right. Okay. Now, the counterpart of a decision problem actually is a language. So that's the only part I will touch language. So formally, a decision problem typically we use this Greek letter to denote a problem, pi, p. So pi sounds close to p, okay, pi, to denote a decision problem. Formally, it consists of two parts. It's a domain of instances. All right, so a decision problem has its domain of instances. So these are valid input. So this one denotes valid input. If you think about algorithm, so that will be valid up. What a legal instance, all right? Now, so each is an element. For example, clique problem, vertex cover problem, each is a pair. It's G, a K. So each is this way. So maybe I use a subscript. So maybe G1, K1, G2, K2, G3, K3, and so on, G4, K4, and so on. All right. So that's a set of instances. That's called the domain. And then for some, the answer is yes. For some, the answer is no. So some may be yes, some may be no. So this one may be no. This one is yes. So this yes and no partition set into two parts. One is yes part, one is no part. All right. So it's a partition. It's good enough to just specify yes instances. So if we know yes instances, we know no instances. So therefore, to fully specify the problem, what we need is domain and a subset of yes instances. That's a formal definition of a decision problem. So that coincides with the definition of language. So language, that's corresponding to a language. This Y pi is a language. It's defined a language. A language is a set of strings. The formal definition of language is just a set of strings. So each instance is represented by strings. So this one is just a set of strings. Okay. Yeah, the size of the domain will be infinite. All right. Actually, the size of the the subset y pi is also infinite. Okay. All right. So this is a formal definition of a problem. It's related to language, but I try to avoid this level. I try to stay away from language level as far as possible. Typically, we stay on problem level, but it's better to understand that the mathematical foundation of a decision problem actually is it's language. It's a set of strings. So that's each member in this set is belong to the language. So answer is yes. All right. So for decision problem, for given instance, you want to know whether this instance belongs to the language or not. To answer yes or no is same as to say whether this string belongs to the language or not. So that's typically how we deal with language when we discuss regular languages, context-free languages, and whatever. That's how we do it. So that's formal counterpart. All right. So for instance, I think I will just give let me see. Oh yeah, I will finish it after give you a formal definition of say vertex cover as an example. All right. So then continue our discussion on Thursday. So for example, the vertex cover problem. All right. So formal counterpart. So it's domain. So if I will use this one to denote its domain, so it contains pair of elements where G is a graph and K is a positive integer. G is a graph. So here is undirected graph. Okay. So K is say positive integer. So that's a formal definition of its domain. And then it's yes instances. That's the language. So that's the language part. So it's corresponding to the following language. It's a pairs such that this pair is yes instance. So G has a vertex cover of size at most K. So in terms of languages, it's contain all yes instances. No instance not inside the language. Okay, so that's a formal counterpart. Later on, I try to avoid this one as much as possible, not go down to the language level, just stay on problem level. All right. But it's better to understand the underlying mathematical structure. That's a language. All right. So I think I will stop here and continue on Thursday. Okay. All right. The upload for homework 3, I will put it up very soon. Yeah, even before the lunch. Okay. All right. Okay, you have 3 more days to finish it for homework 3. Homework 4 will be postponed. I don't know when I will post it because this week certainly we haven't discussed NP completeness. Next week, reading week. Next week, holiday. So you can really enjoy long holidays. Okay. All right. So no class next week, right? Am I right? Reading break. Or you want classes? I guess I'm not allowed to do classes next week. Do I allowed? I will check with department. I would like to give you classes, but the reading week, I don't think I can do it. Are you? I can. I will check with department. Okay. So if legally I can do it, then I will do it. Otherwise, I will not. Oh, that's no. Of course, I can do it anytime. If I can record the classes, then I can do it anytime. Okay. I mean legally whether I can do it or not. Because if some students think they don't want to have classes, perhaps I cannot. Right? That's a problem. Yeah, if recorded, I can do it anytime. So then it's better if I cannot finish things, I can do it in makeup class time during that week. All right. Okay. So I check with department whether I can legally have classes next week. Otherwise, I assume we cannot have classes. Machine learning have classes. I check with department whether it's okay or not. Unless they said no, I think I want to give classes. Okay. Anyway, see you on Thursday. I'll let you know. Okay. Yeah, take care. Bye bye. Time for lunch. 3 straight hours is too much, I think, because I don't want you to read my notes. I want to think. If 3 years is 3 lectures, actually it's a lot. I need to prepare things in advance. I don't have as good memory as you. Like a 1 hour lecture is very easy for me. I can basically remember everything. 2 hours is kind of tough, but 3 hours is too much. Okay. All right. Okay. So time for lunch. We'll see you on Thursday. Take care. Bye bye. Any questions? Bye bye.